Okay, so we've gone over this question before, but Ramila said that the lady that's doing the 5-hour cram session said that she recommended going over it one more time just because it has a lot of aspects that are very, very likely to be on the exam. So I'm just going to go over this really quickly with you guys. And yeah, so just give me 1 second to set this up. Okay, so this is from 2017, and it is an experimental design question, very similar to maybe something that you're going to get tomorrow. So we did a couple of questions with this on Kahoot, but I'm just going to go over it with you one more time for those of you that missed it, or those of you that just want to go over it one more time just to make sure that you have it, jam-packed. So the question says, in flowering plants, pollination is a process that leads to the fertilization of an egg and the production of seeds. Some flowers attract pollinators, such as bees, using visual and chemical cues. So with that, when a bee visits a flower, in addition to transferring pollen, the bee can take nectar from the flower and use it to make honey for the colony. So it says nectar contains sugar, but certain plants also produce caffeine in the nectar. So caffeine is a bitter tasting compound that can be toxic to insects at high concentrations. But to investigate the role of caffeine in nectar, a group of researchers studied the effect of 0.1 micromolars of caffeine on bee behavior. So the results of the experiment to test the effect of caffeine on bees' memory of a nectar source are shown in table 1. So it shows you this table. Tomorrow you are almost guaranteed to have a table or a graph. But it might even be both. You might get a table and a graph, but it's pretty much 100% guaranteed that you will get at least one or the other. So make sure that you understand how to look at data and, make conclusions from it, be able to get your experimental design points for that. So you need to know positive control. Positive control is something that it's a control that you use when you know that the what you're testing is going to be positive. So for example, if I am testing the effects of caffeine on high blood pressure, my positive control is going to be something like a blood pressure pill, like a blood pressure boosting pill, like a pill that I absolutely know for sure is going to increase blood pressure, because I don't know if the coffee does that, if caffeine does that, but I know for sure that pill will increase your blood pressure. Whereas a negative control is something that you know will produce no result. So for example, if they drink water instead of the coffee, or decaffeinated coffee would be even a better negative control, because you know that doesn't have caffeine in it and it should not increase their blood pressure. So you need to know for sure the differences between positive and negative controls. You need to know standard deviation. You need to know standard error, like what those are, what they mean conceptually, more so than being able to calculate them, even though you might have to calculate them. The formula sheet that I gave you has standard error and standard deviation on there. So if you want to practice with those a couple of times, that might be helpful for you. But anyway, okay, so we have this table and we need to make a graph. You guys probably won't have to make a graph, but I'm going to make it anyways, just so you know conceptually like how we got there. So you might end up a step ahead, like in the test. It might be that they give you a graph that already has the error bars. That's a very, very real possibility. So the first question says, on the axis provided, construct an appropriately labeled graph to illustrate the effect of caffeine on the probability of bees revisiting a nectar source. So we're testing their memory based on the caffeine that we're giving them. So we're going to construct a graph. It gives you standard error. So you know that we're going to be constructing error bars. Those are really important. And then it gives you the time, the time that they do. So it says 10 minutes and 24 hours. If you see time on a table, most likely that will be the x-axis. And then the y-axis is always going to be your dependent variable. So what changes throughout that time frame. and throughout, what changes based on the treatment. So your independent variable will always be x-axis, and then your dependent variable will always be the y-axis. So I'm going to write that down. So your independent variable, whoops. Your independent variable, meaning what I change. So something that I'm changing, which is why it has an I, or it's not why it has an I, but that's how I remember it. What I change. And it's going to be on the x-axis on a graph. So if it asks you for the independent variable and you can't figure it out, but the x-axis happens to be the treatments or the time, then that is your independent variable. And then we have dependent variable, which is what is dependent on what I change. So this changes depending on what I do with the independent variable. So your dependent variable is going to be on your y-axis. It's the end result of your experiment. It's what changes because of what you change via your independent variable. So anyways, so we're going to graph that real quick. So we have this really raunchy axis. Just pretend that this is a to scale. Okay, so we look at our scale real quick, and it goes, because it's probability, because our dependent variable is going to be the average probability of revisiting a nectar source. Because it's probability, it's going to be a decimal, because probability is going to go from 0.00 to 1 being 100% probability, 0.72 being like 72% probability. So anyway, so our scale is from 0 to 1. So I'll put, let's say, like 0.2 here, 0.4 here, 0.6 here, 0.8 here, and then 1. And our control, we have a control and the caffeine treatment, and then we have time, 10 minutes and 24 hours. So there's only 2 time frames on here. So the way that you should be doing it is, I'll just do, the 10 minutes. Again, time is almost always going to be on your x-axis, and then we have 24 hours. So it's not a continuous amount of time. It's just they only did 10 minutes and 24 hours, so you're just going to have those 2 points. And then you have a treatment for each of them and a control for each of them. So I'm going to do control in pink. So if it helps you, I'll just put a key right here. So this is the control. And then I'll do the treatment for the caffeine, which is the treatment, in green. I don't know why that just made a line all the way down the thing, but anyways. So pink is control, so I'm just going to graph the control. So it says 0.72, and then it tells you that this is plus. It also gives you the plus or minus 2 standard errors. Standard errors just means that it's giving you a range of means, because just because you got a mean, say, if I averaged the population, like their favorite color or something, or I don't know, like their favorite number or something, and I got a mean of 10, that doesn't mean that everybody has the mean of 10. That just means that that within your population, that the mean is 10. So it's just saying that with 95% confidence with the standard error, and I'll show you that in a second, that the mean is going to fall between your standard errors. So it says 0.72 is the mean, so I'm going to graph 0.72 as a bar graph. So 0.72 is going to be, here, I'll do these. So this is 0.7. So 0.782 is going to be right above that. And then it says plus or minus 2 standard errors. If it doesn't say that it's 2 standard errors already, you need to make it 2 standard errors because otherwise it's not as accurate. So if it gives you a standard error, make sure that you multiply it by 2, and then you're gonna be good to go. So it says it's already plus 2 standard errors, so we don't have an issue with that. So 0.09 is the plus 2 standard errors. So I'm going to go down 0.09 and then also up 0.09. So 0.72 minus 0.09 is 0.63. So that's about 0.63. And then 0.72 plus 0.9 or 0.09, sorry, is going to be 0.81. So I'm going to go right above 0.8. And that's going to be my my error bar for this control. And then the control for 24 hours is 0.41. So I'm going to graph that. 0.41. It's about 0.41. And then the standard error, the 2 times standard error is 0.07. So I'm going to go 0.07 down. So 0.41 minus 0.07 is 0.34. Yeah, 34. 0.34 is right here. So let's do that. And then it's going to be 0.41 plus 0.07, so 0.48. 0.48. So like that. So that's just the error bars for that one. And then I have the treatments that I got to do. So for caffeine, for 10 minutes, it's 0.83. So I'm going to do 0.83. I'm going to graph that over here for 10 minutes. Let's say right here is 0.83. I'm going to erase this little weird line. And then the standard error is 0.07. So 0.83 minus 0.07 is going to be 0.76. So, and again, this isn't super to scale, but I just want you guys to be able to see this. So like that, maybe something like that. Here, let's do that. And then 0.83 plus 0.07 is going to be 0.9. So it would be like that. And then for the 24-hour one, we have 0.78. 0.78. And then plus or minus 0.08. So 0.78 minus 0.08 is 0.7. So that'll be even with this guy. And then 0.78 plus 0.08 is going to be 0.86. So like right there. So that's your error bars. So we have a beautiful graph. We can say this is time. Well, actually, it already says 24 hours and 10 minutes. So this will just be your control caffeine, 10 minutes, 24 hours. And then this is probability of memory. Okay, so we have this beautiful graph. So that was the first question. Again, you might not have to do this, but I just wanted to show you what it looks like. So again, so the middle part is going to be your mean for the memory for each of those. So they probably did multiple Bs, right? So let's say they did like 30 Bs. So out of the 30 Bs, the mean or the average was the point. Let's go back. 0.72 for the control for 10 minutes and 0.83 for the caffeine for 10 minutes. So that's the mean. And then we know that the real average is going to be in between here. That's why we have error bars. It's just showing that statistically, the mean is actually probably closer to somewhere in between here. It doesn't, or it's not exactly this mean, if that makes sense. So it's with 95% confidence that your mean actually falls somewhere between these error bars. With that being said, the mean, just because the mean is lower here and higher here, because they overlap, that means that the real mean could be like here, which would match with this mean, or vice versa. This could be lower, which would match with that. So the whole basis of error bars is to see if things are statistically different or not. Okay, so we'll go to the next question and I'll explain a little bit more what that means. So it says, based on the results, to describe the effect of caffeine on each of the following. So it's a short-term memory of a nectar source and long-term memory of a nectar source. So with short-term, or 10 minutes, we have error bars that overlap, meaning that their means might be the same. And if their means might be the same, then we can say that there is no effect on memory for the bees via 10 minutes. So I would write something like, for B, I would write B here. For B, I would write there. You don't even have to write, I don't even think you have to write significant. But the whole point is there's no significant, or there's no difference or effect. There's no effect of caffeine on B's memory. Oh my gosh. Short term. But if you look at the 24 hours, you have means that are vastly different, and your error bars do not overlap. So these obviously overlap, but these do not. We have this giant gap right here, and these do not overlap. So if you go parallel and there's another error bar that overlaps like that, then there is no difference, no significant difference. But since these overlap, then there absolutely is a difference. So we can say there is a significant effect on, or sorry, of caffeine on and that's going to be long term. If I can, I don't know if it'll let me, hold on. Sorry, so there is a significant on the bees' memory. Long term, sorry, make sure that you specify of caffeine. And then say caffeine increases bees' memory long term. Okay. And then it says describe or design an experiment using artificial flowers to investigate potential negative effects of increasing caffeine concentrations in nectar on the number of floral visits by bees. So identify your null hypothesis and appropriate control treatment and the predicted results that could be used to reject the null hypothesis. So when you're designing an experiment, you need to obviously have a treatment and then a control. So we can say for C, So let's start with the let me make sure. Well, let's just start with the so you might say that you can have or a control that has the artificial flowers with no caffeine. So again, this would be a negative control. I don't think that it doesn't ask specifically for you to say that, but this would be a negative control in case it does ask specifically. Because there's no caffeine, then we know that there's not like something that would nothing should happen. So that's a negative control. So you can have a control with artificial flowers with no caffeine, and then your null hypothesis always is going to be that there's going to be no effect or no difference. So no significant difference between between the bees' memory without the caffeine and with the caffeine. So no significant difference. That would be our null hypothesis. And then also asks for you to do predicted results. So we would predict that the bees' memory would increase with the presence of caffeine. Be careful with this because we're not increasing caffeine levels. We're just going to have either caffeine or no caffeine. So with the presence of caffeine, not with increasing caffeine. Just be careful with your wording. And then you can just explain your overall experiment, like what it would look like, what your independent and dependent variables would be. I don't know exactly when it says design experiment what exactly it wants. I can look in just a second. But basically, you can just explain the rest of it. And then it says researchers found that nectar with caffeine tends to have a lower sugar content than nectar without caffeine. This is one of the questions that would be more of ecology based, so I don't think that you're going to get this question. But it says plants use less energy to produce the caffeine in nectar than they do to produce the sugar in nectar. Propose one benefit to plants that produce nectar with caffeine and lower sugar content, and then propose one cost. So a benefit would be again, it says that it is less energy, so that is your number one benefit. That it's less costly or less energetically costly. And your cost would be. Okay, sorry, I'm going to read it. Researchers found that nectar with caffeine tends to have a lower sugar content than nectar without caffeine. Plants use less energy to produce the caffeine in nectar than they do to produce. It says lower sugar content. Obviously, plants need or they don't need sugar, but like they produce sugar. And the bees need the sugar for energetics. So the bees would get less energy because they need that sugar. They need that glucose for energy. Get less energy from the bees. Or from the plants, sorry. Bees would get less energy from each of the plants because there's not as much sugar. So that would be your cost. I think that's the whole question. Yeah, so that is the full question. I just want to go over really quickly the I haven't actually looked at the scoring guide, so I just want to make sure that I didn't miss anything. Yeah, so you should have gotten points for graphing. If it were to tell you to graph, I obviously don't think that you're going to have to graph, but you would have gotten points if you were to actually do this question for the correct graph. And then describing the effect of caffeine on each of the following. So short term, you should have said that caffeine does not affect short term memory or memory at 10 minutes. And then long term, caffeine improves or increases the long term memory at 24 hours. So we did that. Perfect. And then it says design an experiment using the artificial flowers to investigate potential negative effects of increasing caffeine concentration. Oh, I didn't. Okay. Whoops. I did that wrong. So it says using artificial flowers to investigate potential negative effects of increasing caffeine. So this is a good example of why you should read things before you go too far into the question. So it's asking you to design an experiment that's different from this experiment that investigates potential negative effects of increasing caffeine concentrations. So obviously you would need to do multiple treatments with increasing concentrations of the caffeine, because in the other experiment they only did the 0.1 molar of caffeine with the absence or the presence of it. So what you would have to do for your null hypothesis, what you would put for your null hypothesis is that increasing caffeine concentrations has no effect, so it wouldn't have any negative effects. It's the same thing as the null hypothesis I just showed you, but it's just a little bit different in context. And then your control would be the nectar and the flowers with no caffeine again. That's the same thing as what I put. It's just in a little bit different context. And then predicted results will actually be a little bit different because I wasn't reading it correctly. But for the predicted results, you should have put that the number of floral visits by bees is different at increasing caffeine concentrations. And then the number of floral visits by bees is different than the control. So it needs to be significantly different than the control. Yeah, so you just needed to put with increasing caffeine concentrations, we expect a different number of floral visits by bees. Yeah, perfect. Okay, read your questions, folks. And then again, the one benefit would be that the more you can say that the more pollen is transferred, and also the plant stores energy and has more energy available for other uses, so it's less energetically costly for the plant. Whereas for the bee costs would be that the bee would use more energy, and then it's that I mean the plant is also producing less energy, so the bee would get less energy from that plant. Okay, that's it for that question. Forgive me for reading it wrong the first time, but anyway, so I just wanted to show you guys that question because it is very, very common. Like the concepts for experimental design are very common, and they're probably going to be on the exam. So yeah, that's it. Have a good night, guys. Good luck.